Today we'll talk about integrity, integrity, authentication, and key management, which is part 3 in the book. And we'll start talking about message integrity and message authentication. Message integrity and message authentication. So let me go to my PowerPoint.
That's good.
No, we're going to move that. So you're going to carry it on top of the wireless. Move that.
No, there.
Yep. Thank you so much. That's good. That's good. Thank you. Thank you so much. So nice of you. So, go ahead. Thank you so much for coming. So, today we'll talk about message integrity and message authentication. A very important security tools that we use. All right. So, what is message integrity? Has to do anything with message privacy? So we need to make sure the message is integral. So if I send you, for example, a message, no class today. Okay, do I need it to be encrypted? Do I need to be private? No. Okay, but what I need it to be? Integral. The integrity. So I don't need somebody, for example, to change it. No, there is. For example. So many times we need to make sure the message is not encrypted, not secret. We need to be integral. That means nobody alters it. So when you receive a message from me, the first thing you're gonna ask yourself, oh, he did send this message? Is it the right message? Is it integral? Did anybody, change the message? Okay? Think about like the well. Well. People die, they have a well, all right? So you need to make sure that the well is integral. Okay, nobody has changed it, right? So how we do that? Okay, how we do the message integrity, guarantee the message integrity and message authentication. All right? Authentication. The message is authentic. Message authentic. That basically happens through hash functions. Hash functions. All right? And we'll see how we can create something called digest. Digest. So in simple words, you have your message, you're gonna pass it to a hash function. Okay? The hash function will give you a digest. Okay, digest. Okay? The message could be, for example, it could be 2K bits. Okay? Any size. But the digest is a fixed size. So let's say 128 bits. So what you do, you send the message and you attach to it what? The digest. Okay? This digest is like what? Like your signature. Okay? Signature. Alright? When it arrives at the destination, what they have to do? Calculate the digest again. Okay? Of the message. Okay? Compare it with the one sent. If they are the same, then the message is integral. Okay? Okay? So there is different techniques, different algorithms for that. So again, remember that when we started with talking about encryption. So far we're talking about encryption. So we have divided the whole world to synchronous encryption and asynchronous. Or we call it a private encryption and public encryption, or one key and two keys, right? And all of these algorithms, according to Kirchhoff laws, are public. Everybody knows all of these algorithms. What we are trying to hide? The keys. The keys, right? And we have also to have a complex algorithm. The more the algorithm is complex, the much more it will be more complex to decrypt it, right? To break the code. Same thing in here. We're going to talk about a few different hash functions that we're going to apply. Okay, hash function could be with a key and could be without a key. Okay, if it's a key with a key, it will be much more secure. But in this case, also you have to do what? To share the key. Share the key. So it could be a simple. So let's fly together and see what we're gonna cover today. Okay. It's good. One more. Good. Like this. Your call.
Yeah, that's
Like this. Good. Okay. All right. All right. So cryptography. Okay. Let me just fix this. Okay, so cryptographic system means that we have studied so far provides security, okay, confidentiality, but not integration, not integrity. You need to talk about how can we make our data integral. So one way to preserve the integrity of the document is through using fingerprint. That's when you go to the bank, okay, you have to sign by your hand. So that's what we need to do with our documents now, but digitally. How can you guarantee that your document is integral? So using the electronic equivalent fingerprint, we could have the message. As you see in here, we have the message. We pass it to a digest, to a hash function, and we'll create a fingerprint, which is, we call it a message digest. All right? As simple as that. All right? Is there more? So, what is the difference? What's the difference between real fingerprint and digest fingerprint? In the real fingerprint, your signature is attached to the document all the time. In here, they are separate. You could send the document by itself, and you could send the digest by itself. You need to make sure that document is the correct, is authentic. You have to check the digest, okay, again, and try to compare between the one you regenerated and the one was sent. If they are identical, then it's correct. So the message digest needs to be safe from change. All right. So let's say that I have this current message. It passed to a hash function and it created a current digest. All right. So if I have a previous digest, which is the authentic digest, and I could generate, I could compare it with this digest. So you compare this with this, right? Okay, I compare this with this. Okay. If they are the same, then the digest. If they are the same, then message not changed. It's integral. Okay. If there is a change, then the message is not integral. Has been changed. Right? Okay. The same thing with real documents, with your bank document, with any document. Okay. With your check. When you write a check, it goes to the bank. You have to sign it, right? So what the bank's supposedly to do to compare the signature on the system to the signature on the check. If they are the same, then it's valid. If it's not the same, then it has changed. It's not true, right? That's exactly what we are trying to do in here. So cryptographic hash functions, that's what we use. We use the hash functions must satisfy 3 criteria. So now in this class, what we're gonna do, we know what we need to do. The goal is to make sure the messages are integral. That's number 1. How we do that? By calculating that, the digest. How we calculate the digest? By using a hash function. Alright? So we're gonna learn about a few different hash functions. Right? Exactly like before, we have learned about a few different algorithms for public encryption and private encryption. Right? Here we're gonna learn. But we need to know the goals. What this hash function must have. What are the criteria must have that we could use them. Alright? Right? So the first criteria is it has to have something called preimage resistance. We'll explain it. Secondary preimage resistance. And number 3 is collision resistance. Collision resistance. Alright? So for example, if I have a message in here, okay, and let's say the digest, let's say the digest is 128 bits. So how many different digests I could have? 2 to 1 to the power 128. You agree? Different digests. But if I have the data is like 1K, for example, which is like 10 to 24 bits, right? How many messages I could create? 2 to the power 10, 24. All right? So the problem in here that many messages will have the same digest. So you could regenerate, you could reword this message that could give you the same digest and send it. Then the receiver will not be able to know it's a fake message. Why? Because like 2 messages conveying 2 different information, but they are generating what? The same digest. Alright? And that's a problem. That's a collision, right? That's a problem. So how we solve this problem? How we solve this problem? Alright. So the first condition is to have a preimage resistance. What is a preimage resistance? Very simple. Okay? If you have, look in here. So M is the message. M is the message. Then you hash. Then you have the Y. What is Y? What's Y? The digest. Y is the digest. So hash is a function. You pass for it the message. Will give you Y. What is Y? Digest. I need you guys to talk to me. Okay, I don't want to be the only person to talk. Right? The reason why I want to talk to me because I want to make sure everybody's awake. Why I want to make sure that everybody's awake? Because if you are not, I have to wake you up. Why I have to wake you up? Because I feel the obligations inside me that I don't waste your time 3 hours. I know you can get bored. Maybe I'm a boring person, but my job is to make you with me the 3 hours, right? As much as I can. All right. So when I ask a question, please help me out. Shout out. All right. So we have M, which is the message, a block of a message. Hash. What is hash? Is a function. What is Y? Is that digest. So we're gonna pass. It's a function. We're gonna pass the message for it. It will gonna give us what? The Y, which is the digest. So that's who. That's like Alice. Alice will send it. All right, to Bob. Will send to Bob. So let's say that the person knows Y, and from Y can finds the M, can find the message. All right. Is that a problem? That's a problem, right? It has to be one-way hash function. What does it mean one way? That you could, from the message, generate the digest. But you should not be able to generate the digest from the message to generate the digest. Alright? It has to be one-way function. So it has to be one-way hash function. So you're trying in here to find the message such that Y equals the hash of the M message, M prime message. So what is M is the real message. What is M prime? The message that you're trying to find. Okay? So that is the preimage resistance. So let's take example in here. Can we use the conventional lossless compression? You know what's compression, right? There's different algorithms in compression. So compression, you have a file, you compress it. All right? There's two categories for compression algorithms. One of them we call it lossy, and one call it lossless. Lossy, that when you compress, you cannot bring it exactly to the same previous shape. It's lose some of the information, lossy. And the other one is lossless, okay, that you could decrypt, you could compress and decompress, and it would be exactly the same copies. All right? All right? So that's lossy and lossless. So let's say we are talking about here lossless, okay? Compression method creates a compressed message that is reversible. So the question is, the question in here, can we use this conventional lossless compression method, such as stuff_it is one of the algorithms, as a cryptographic hash function? Can we? Yes or no? What? Speak up.
Are they talking about checksum function?
It's you have a lossless function. You compress it and decompress it back. Can we consider it as a digest, as a hash function? Why? Why? It's no. Why? Because it's not one way. The hash function has to be one way. In here we could go both ways. If I have the compress, I could go to original data, and if I have the original data, I could go back to the digest. So compression techniques, are they considered one-way hash functions? No, I cannot use it. Go to the second question here. Can we use a checksum? You know what checksum? Like CRC? Checksum, like, you know, in DCC, you took a DCC, you know, calculate, you know what checksum, right? Yeah, well, checksum is basically what you do, like the CRC, for example, in DCC, or in, you know, when you transmit data. So in communication, when you send a frame, for example, right? A frame, whatever it has, that's frame, right? It has data, right? So you need to check the integrity of the data. What you calculate with it, some called CRC, or checksum, right? So this is what's calculated from this. When you send it to the destination, source to the destination, okay, all right? So the destination will receive the whole thing, okay, with the CRC. So it will calculate the CRC prime, the second one, and compare them if they are equal. The one received and the one sent, right? If they are equal, then the message is integral. If not, they are not integral. That's what is checksum in communications, right? So can we use checksum? Can we use checksum as a hash function? We cannot. A checksum function is not preimage resistance. Eve may find several messages that would produce the same CRC. So when you have several messages could produce the same CRC, then it's not a preimage resistance. What's a preimage? That you could imagine another message that gives you the same digest. Okay, so they are not. So checksum is not, you know, it's not. Moving forward, okay, in here, then the second condition is second preimage resistance. So in here we have again the message M and the hash function. So you see the M, we produce the hash, and then now what we send the message with the hash, with the digest. We send the message with the digest. Alright? So what will happen, this guy in here received the message with the digest, it tries to find message prime that it's not equal to M, but will give you the same digest. So the hash of M equals the hash of M prime and m does not equal m prime. That means two different messages gave you the same digest. That's not accepted.
Like, what do you mean by sending the message with the hash? Are we sending the actual?
So you're gonna send in here the message plus the digest. Message plus the digest.
So we are sending the message.
You're sending the message plus the digest. Message, we generated the digest. Then we form one packet like here. We have a frame with CRC attached together. And here we have a message with the digest. So the enemy received the message with the digest, not the digest alone. In the first case, the enemy, okay, received the digest by itself. Then he tried to find a message that could produce that digest, and he received both. So now what is he trying to do? Trying to find another message that will produce the same digest. So when this another message you send it to Bob, Bob what will do? Create the digest again, okay, from the M prime. Is M prime the correct message? No. Does it give you the same digest? Yes. What Bob will do? Will take it or refuse it?
Take it.
Will take it. Why?
Because
the same digest.
Same digest.
All right. So this guy in here was able to find a different message that generated the same digest, and when the digest went here, it was the same, generated the same, but it's a wrong message. So that's what we call it, the second pre-image resistance. It's not second pre-image resistance.
So how come they got to generate like a different message since they already have a message with the calculations?
Say it
So
again.
they get this one. Like how come like we generate different message when they have like a message and a digest together?
How come? Okay, because So you have a message and you have a digest. All right. So let's say the message, very simple. Let's say the digest here, it says, okay, I love the Bridgeport. Okay, and generated this digest. Let's say the digest in here 1-1. Okay, and let's say the message, whatever in here. Okay, and let's say the message, I love Bridgeport. Fair? Generated this digest. So now when you send, what you're gonna send? The message with the digest. The guy in the middle hates Bridgeport. Does not love Bridgeport. And he needs to convey the message to Bob, I hate the Bridgeport. I don't love Bridgeport. So he was able to design a message, a different message, that will produce the same CRC and send it to Bob. So Bob receives what? What does Bob receive? Talk to me. What Bob receives? The message that I hate Bridgeport. Is it the correct message? No. Is it the same digest? Is it the correct digest? Yes. So Bob would be what? Fooled. So that's a problem if you have a function that could generate same digest for different messages. Alright? Why is it a problem? Because the goal in here, we have to make sure the message is integral, the same message. So there's people who could play with the algorithm to generate a completely different message, but generate the same digest. Then the whole thing is mute. The whole system did not work. You could round it. So if you are using a hash function that we could go around it, that's a problem. Don't use it. All right? All right. That was a good question. Thank you. Okay, let's take now the collision resistance. What is collision resistance? If you are given none, so the enemy is given none, okay, or the cryptanalysis, whatever. Okay, so you need to find m prime, which is a new message, different than m, such that the hash of m equals the hash of m prime. Okay, and this is just absolute collision without information. Okay, and this is, by the way, expected. Why? Because the size of the digest is much more smaller than the size of the packet. Okay, so the message. So let's say that the size of the digest is 2 bits. Okay? Okay, and the size of the message is 3 bits. 3 bits, right? How many messages we could have total? 6. 8. 2 to the power 3 equals 8. How many digests we could have? 2 to the power 2 equals 4. So that means, in average, every 2 messages will have the same digest. Right? Makes sense, right? Okay, so yeah. All right. So this are 3 conditions. So let's talk about random oracle model. So the random oracle model, which was introduced a long time ago, in 1993, is an ideal mathematical model for functions. So now our goal. Let's go from the very beginning. So what our goal in here? We need to have message integrity. How we can do the message integrity? By calculating a digest which work as a fingerprint. Okay. How we create this by using a one-way function. So let's talk about the one function. It has 3 conditions: first image, second image, and collision. All right. We're moving forward now. We need to see how can we create this hash functions. How we can create these hash functions. Clear so far? Okay. So in here, for example, let's take this example. Assume an oracle with table and fair coin. Okay. The table has 2 columns. So what is the column? The message. Okay, the message. Okay. And the way you generate the message digest is by a coin. Okay. 16 times. How many bits in here? So 4 plus 4 plus 4 is 16 times. Right. 16 times. So if it gives you heads, 1. If it gives you 0, it's. If it gives you tail, it's 0. So randomly you are generating what in here? The message. This is not a mathematical model, it's like experimental model by the coin. So the message, for example, in here, AB123, whatever AD, okay, is given for the digest calculation. Okay, the oracle checks, it does not have it. Is it in here, in the table? It's not. So it has to go and generate it again. It has to be generated and added to the table. So what you do, the same now in here, you calculated you did the flipping 16 times for this, and you come with a digest. Where is it? It's in here. So we added this line with the digest. Now, the message, which is this message, all right, okay, is given for the digest calculation. The oracle checks its table and finds that there is a digest for this message. Where is it? The first one. This one is the first one. It's gonna pick what? The digest. So that's the message, that's the digest. Okay, in the first one. The oracle simply gives the corresponding digest for it. So, okay, so basically you have a table of messages and digest. If you are asking for a message that does not have a digest, what do you have to do? Calculate it and add it to the table. Okay? If you are requested a message that already is in the table, what are you going to do? Give the digest. Dig up the digest and give it the table. Alright. Okay, so the oracle example in the previous one cannot use a formula or algorithm to create a digest for a message. It's just flipping a coil 16 times. For example, imagine the oracle uses a formula which is hash of the message give you the hash of the message give you the message mod n. So this is a formula. It's not experimental. It's a formula. So if I need to calculate it, okay, it will give me. Okay, you know, right away when you look at it, when you use modulo, is there a problem? It repeats itself every.
For reminder.
Yeah, because a modulo. It repeats itself every.
But we can use either linear probing or checking also. With the same key we can store the multiple values.
But repeats itself every. And
Every
here
time with the same key.
every m, right?
Yeah, we need to have a different keys.
Exactly. Okay, so it will repeat itself every n. All right. That means, you know, we're gonna have many messages that having the same
Same key.
digest. In this case, it's digest, right? So now suppose that the oracle has already given MHM1 and MHM2. That's a problem. It's a different problem we're talking about. All right. So you have the digest for M1 and you have the digest for M2. And let's say that you are given M3. All right. So there's two ways. You go calculate the M3. Of course, I mean, we talk about M1 is like a big message. It's not like 2 numbers or 3 numbers that you could do it, okay? Let's say M1 is given to you and M2 is given to you. You are now given M3, which equals the addition of both of them. Can we calculate the digest for M3 from the other 2 digests? Sure we can. So what we'll do in here, it will be like the hash of the M3 equals M1 plus M2 mod n. You have already this and you have this, then you'll be able to calculate it. So in here we were able to calculate the digest of a different message because it equals to the addition of other, or subtraction, or multiplication of other 2 messages. Alright, so this relates the third requirement that each digest must be randomly chosen based on the message given to the oracle. So this is called collision. It's called collision. Alright? What does it mean, collision? That means that if it just happened that you have the digest of 2 different messages, you were able to calculate the digest of the third message because you have the other 2. So what we call this? Collision. Is that good? Not good. It's not good. What does it mean, not good? Not good means what? Not secure enough.
Yeah.
I hear you. I hear you before you talk. It's not secure enough. Okay? It's not we are like racist against one technique. It's like not secure enough. I mean, our goal to have it secure enough. Clear so far? Okay, good. Alright, so if n, okay, so now let's take a look at the security of these things from different perspectives. Take a this problem. This is a statistics problem. Okay, you'll find it in the statistics box. If you have n pigeonholes, okay, pigeonholes, okay, are occupied by n plus 1 pigeons. So you have holes, and you have n plus 1 pigeons. So that means one hole will have how many pigeons? 2, right? So then at least 1 pigeonhole is occupied by 2 pigeons. I mean, of course, you could have all the pigeons in one hole if it's allowed, but not the story, right? Okay. So the generalized version of the pigeonhole principle is that if n pigeonholes are occupied by k plus n, kn plus 1 pigeons, then at least 1 pigeonhole will have how many? K plus 1 pigeons. K, okay, plus 1 pigeons. Okay, and that's what we're trying to solve in here. Okay, what we're trying to solve in here, that you have, this is all the pigeons, okay, and these are the pigeon hole, right? The other way. These are the pigeons, and this is the pigeon hole. So you will find more pigeons in the holes. Okay. In other words, in our talk, that you'll find different messages have the same. No, I'm asking same what? Digest. Okay. Same thing. Thank you. So, all right. So, and here, go in here, assume that the messages in the hash function are 6 bits long. So we're talking about in here what? The messages. Assume the messages. So if we have 6 bit long, how many total different messages we could have? 2 to the power 6, which is 64. All right. 6 bits. The messages are 6 bits, right? Okay. What? Assume that the messages in a hash function are 6 bits long, and the digests are only 4 bits long. So how many different digests we could have? 2 to the power 4, how much? 60, right? Alright. So, and the possible number of messages are 2 to the power 6, which is 64. That means n equals 16. And kn plus 1 equals 64. okay, n equals 16, n digest, n pigeonholes, okay, so it will be kn plus 1 64. So k is larger than 3. The conclusion is that at least one digest corresponds to 4 messages, to 4 or k plus 1 messages. Okay, 16 and 64. Okay, that means you'll find that for each 4 messages, 1 digest. All right. Okay, the idea here is calculating what? The k. Okay, k plus 1 equals 64. What is k? K times n, I'm sorry, plus 1 equals 64. All right, so the k, it will be more than 4. More than 4. So there is 4 problems. There is 4 problems. The birthday problem. Again, this is from, you find it in the statistics book. Okay, so we want to see how we can apply it to our. Okay, so the 4 birthday problems. The first one, as you see it in here, okay, and what does it say? The first one, it says, what is the minimum number k? Remember, they're trying to solve for k, right? What is the okay, again, in here we said that n times k plus 1, all right? Okay. So the question is in here, in the first problem, it tells you what is the minimum number k of students in a classroom. So you have a student's classroom. This is set of students, and we are talking what we call the problem of the birthday. We are looking for the birthday match. Okay. So the first problem. Okay. There's another keyword you have to know when you say likely. What does it mean likely? There's a chance 50% or higher. That means the property is greater than 50%, and than 50%. So the first one, if you have a table like this, the first part of the table, and you have a predefined value, a predefined birthday for a student. So the question is, what is the minimum number k of students in the classroom such that it is likely? Again, what does likely means? 50% or higher. Okay, that's what likely. Likely that at least one student has a predefined birthday. Let's say, for example, June 1st. The predefined value June 1st. All right. What is the likelihood? That means 50% chance that one of these students have likelihood 50% of the higher. All right. That depends on what? It does not depend on the birthday.
The
Number of students. The k, no, number of students. So let's say, what is the chance? What is the likelihood? Again, likely means
50.
huh?
50%.
50% or higher, right? Likely 50. What is the likelihood that one of us born in July 1st in here?
So near the month they used to target it.
Huh?
Whether the key is used to target on month or is it?
Yeah, month or not the year.
Okay.
July 1st.
July 1st.
Okay.
So it probably take the person who born on July.
Sure. I mean, like here, how many we are here? 20.
20.
What is the likely? That means 50% chance that we'll have one person born on July 1st. So let's say we are 20. The chance is low. But if we have 100 people, the chance is higher or lower?
Higher.
Higher. About 300 people.
More higher.
More higher. Okay? So the question is, we are looking for k. So we are looking for a k. So what's the question one more time? How many we should be here? That's k. That there is a chance 50% that will find one student born in July 1st. We don't know. You have to solve for it. That's k. K, we don't know. All right, we don't know. So we know we're looking for 50% or higher. Okay, so what is the minimum number of students in here, which is K? That gives us a chance that we'll have July 1st or 50% chance that one person is July 1st. So we're solving for K. Clear? Clear? What is the K? Let's take a look at the second problem. The second problem, again, all of them 50% or higher, right? Okay, so this is a predefined value from outside. In here, what is the chance that one value in here, let's say we picked July 1st, we'll find another student in the class is also July 1st. So we need to have two July 1st. So you think its K will be higher or lower?
Higher.
Higher. Will be higher. Okay? Alright? Clear to you?
As
Okay.
the probability increases, we can easily find it.
Exactly. Okay, it's high. Right? So that's what is the second one. So problem number 2, what is the minimum number K of students in a classroom such that it is likely, and likely means 50% or higher, that at least one student has the same birthday as the student selected by the professor. Alright? So what's your birthday, if I may ask?
February 8th.
February 8th, right? Close to my wife. My wife is... No, my wife March 10, sorry. Alright, so February 8th. So what is the likelihood, 50% or higher, that we have another person February 8th?
It's gonna be more higher from second one.
You need more students.
More students from the
exactly, from the
yeah.
previous one.
Yeah.
Because now we're gonna get two.
Yes,
Alright?
the chance.
Alright. So the third problem, what is the minimum number K of students in a classroom such that it is likely that at least two students have the same birthday? So we could have at least two students. So same birthday, one or two or three bears, So what is in here? So the same thing in here. So at least, okay, two students have the same. Here only one. It's only one, one occurrence. Here multiple occurrence, right? And the fourth problem here, it says we have two separate classes, right? We have two classes, each with K students. What is the minimum value of K so that it is likely at least one student from the first classroom has the same birthday as the student from the second classroom? So two classes, K students, we don't know K, okay? But we need to know the likelihood, 50% or higher, that if we have K in here and the same K in here, that two students have the same birthday. This is you'll find it in the statistics. Has nothing to do with us, okay? It's okay. So there's calculations. So what we are solving for?
Okay.
Okay. We know what we know. We know the property, which is 50 and higher, and we need to find the K. All right. So we could solve it for you, but it's gonna take us forever to solve these problems. But here's the results, right? So the results for the problem. For the first problem, okay, here, okay, the probability, okay, will be this, okay, and the general value for K, it will be calculated this way, okay, and the value of K with the probability 50%, so we substitute 50% with the P will come, okay, K equals 0.69 of N. 0.69 of N, and the N is the total population. Okay, which is in our case 365. So, in the first, let's go to the back to the example. So let's say that we have 365 students. So how many students I have to have here? that if I have a predefined birthday, I could likely have, I could find a student there.
253.
So when you compensate in here, k equal 169 times n, which is
253.
365, I have to have in that classroom how much?
253.
253. Same thing with the second problem. The math is there. It has to be 254. Okay, the collusion, it will be 23. And for the fourth problem, 16. Okay, for the fourth problem, okay, 16. So,
I think 365 is the number of days on the year.
what?
365 is how many days in the year?
How many what?
Days in a year.
No. Number of students. Okay, it's a number of students. Okay. So that's the solutions in the table. So this one problem represents the first image, and this is second image, resistance, and this represents what? The collision. In our case, represents the collision. Remember that we're gonna have three conditions and all of that. All right. All right. So okay. So when you look at this graph, what you learn. So this, for example, in here, this is the first and the second image. First and second image. As you see in here, as k increases, the probability what? Will increase. But it's not so drastic. It's kind of almost like linear. Alright? How about when you look at the third problem and the fourth problem, okay, if you increase, for example, from 10, the probability is like 20% or 10%. 10, okay. To 20 students, it becomes what? 4. You go 50 students, the probability is very high. Becomes very high. Okay, it becomes very high. Okay. So we'll see the difficulty of a pre-image attack is proportional to what? 2 to the power n. Okay. N, what is n?
Number of students.
Number of what?
Students.
Number of students. In our case, it means what? The size of the message. So the bigger the message, the more resistance first images. Okay. I mean, we could jump to the conclusion, but then we're trying to prove the conclusion for you, right? All right. So a cryptographic hash function uses a digest of 64 bits. So what is the size of the digest? 64. Nowadays we don't use 64 or 128. It's so small. Small. We use 512 and higher. Okay? But this is for an example. How many digests does E need to create to find the original message? Okay? So from the 64, how many total digests we could have? 2 to the power 64, which is a lot. Alright? So how many she needs to create to find the original message with the probability of 50%? Fine. So the number of digests to be created is from the equation we had, right? K for preimage 0.69 2 to the power n. 2 to the power n. How much is n? 64. Okay? So this is a large number. It's a large number. Even if Eve can create 2 to the power 30, which is like 1 million calculations in the computer, okay, almost like 1 billion calculation messages per second, this will take 0.69 times 2 to the power 64 divided by 2 to the power 30, which is will give you 234, right? 2 to the power 34, right? So seconds, which is more than 500 years. Which is more than 500 years. So if you have a digest, 64, okay, bits, all right, and you would like to keep trying messages, okay, with the computer that could generate like 1 billion per second, 1 billion operation per second, how many years are you gonna need? 500 years. 500 years. So this means the message digest of 64 bits is secure with respect to the pre-image attack. We're talking about one image. I mean, there's three kinds of attacks, right? Pre-image, second pre-image, and collision. So in terms of a pre-image attack, it's gonna take you are okay. Okay? How about the second pre-image? You are okay, because again, it's proportional to what? To 2 power n, the same thing, right? If you go to the table in here, so you see in here is proportional to what? Where is it? Okay, to the power n, to the power n. Here to 2n. So let's go here. So in the second pre-image attack, okay, the difficulty of the second pre-image attack is proportional to the power n. So it's okay. When you go to the collision attack, it's proportional to what? To 2 power n over 2. That means it's gonna need half of the time. Okay? That means if the constant is the same, and here it will be 2 to the power what? 64 divided 32. Okay? If you divide it by 30, that means 2 to the power what? 2. So that means very, soon you could break it, right? So the difficulty of collision attack is proportional to the 2 power over n. Alright, so let's take example in here. A cryptographic hash function uses a digest of 64 bits, the same thing. How many digests does Eve need to create to find 2 messages with the same digest with the probability 50%? The same thing. So now you calculated k, which is 1, it's a second preimage, right? 1 times 1.18 to the power 2 over n over 2, power n over 2, which is 2 to the power 32. It's a power, mistake, right? If even can test 2 to the power 20, almost 1 million, so not 1 billion, 1 million even, okay, the message per second, it needs that much seconds, which is less than 2 hours. I mean, if we use like in the previous example, a computer that could do 2 to the power 30, it will be in a few minutes or seconds. So what we conclude that that if the hash function is good in collision property, you don't have to worry about the first 1 and 2 criteria. It will not have to work if it's if it takes like, if there is a hash function that take 500 years to do the pre-image and 500 years to do the second pre-image, right? And gonna take 2 hours to do the collision, the third condition, definitely you don't have to worry about the first 2, it's safe. Let's say we have another algorithm, another hash function that for the collision problem, is safe for 500 years. Do you have to worry about the first 1 and second 1? Of course not. No, because if the third one is secure, the first one and the second one is secure. Alright? So you have to worry about the third criteria, which is the collision. Alright? So the difficulty of an alternative collision attack is 2 to the power n over 2. Here is the problem. The third criteria is the problem. If you secure it, you don't have to worry about the first 2. That's what I'm trying to say. So when you look in here, the summary in here shows the level of difficulty. Okay, each attack, every digest. So for the pre-image is the order of 2 to the power n. And here is to the power of 2n. In here the problem, and the third one is to the power 2 to the power n over 2. So this is what you have. If you have a hash function which is secure enough in here, you don't have to worry about that other 2. So originally a hash function was 64-bit digest were believed to be immune, because we just saw it at 500 years. But when we went to the collision became 2 hours. Okay? So originally, you know, they were believed to be immune to collision attacks, but with the increase in the processing speed, computers are improving every day, today, you know, so it, you know, it's you know, like 64 divided by 2 will give you 2 to the power 32, 2 to the power 32. Okay, this will, you know, will tell you that 64 is not secure anymore. We don't have nowadays hash functions that use at least 512, 1K, 2K, you know, you cannot use this. For example, MD5. Everybody heard about MD5 before? Okay, MD5 used to be very common, okay, which was a very common. It used to be very secure, okay. It's only 128-bit, and we don't use it anymore. It's not secure. It's not secure anymore. How about SHA-1? SHA-1 also, we don't use it anymore. It's 160 bits, the digest, but we don't use it. We use SHA-5. We're gonna see SHA-5 later, okay? So because the digest is small, all right? So SHA-512, we'll see it in the next chapter, okay? It will give you a collision with a probability of 150%. So the adversary may have other tools to attack hash functions. One of these tools, for example, is meet in the middle. Meet in the middle. Try to get either digest or the message, or both, or none, and try to generate things. All right. So, generally speaking, you know, there's two things. There is something called modification detection code. Modification detection code. That means it's a code to detect modification in your message. And there is something called code authentication, to authenticate the message. When you authenticate who? The sender. So the first one just checks the integrity. The second one, authenticate the sender. And how you authenticate the sender? By a key. The person has something belong to him that you could identify it, right? So which one is more secure, MDC or MAC? MAC. Okay, because you do both authentication. All right. So in here, when you look in here, modification detection code. Okay, think about it like this: you have a message that you're gonna send in secure channel. Why we send it in a secure channel? Because we don't care about its privacy. Everybody can read it. Who cares? It's like me sending you a message that for the next 2 weeks there is no class. Go celebrate. Okay? Okay? All right? So it's secure. So what we have to send in a secure channel is the hash. So from the hash we create a message. What do you call it? Modification, whatever code. MDCs, detection code, I'm sorry, message detection code, and you're gonna send it in secure channel, right? This is like, serves like your signature. So the message was received by Bob as a message. All Bob has to do to generate the MDC again, and Bob will receive in a different channel the MDC, compare them together. If they are the same, then accept the message. If they are different, then accept the message. All right. So these are very simple. It's just detection. There is detects. This code detects if there is modification in the message or not. What does it take to do that? You have to send a message, even in secure channel. That's fine, but you must send the MDC through a secure channel. Take a look.
How do you know which message is secure? Which is like that?
How you know it's secure or not secure?
Which one is the modified one? Which one is?
Which one is what?
Like which one is modified and which message is not?
Well, I mean, we just said. I mean, you send the message. That's your message. Let's say the message. There is no class next week. Who receives it? Bob. All right. In a different channel, he will receive what? The digest, which is a small digest. So from the message, Bob will calculate the MDC, and he will receive the correct DC. If they are the same, that means the message is correct. If they are different, then the message is not correct. Right?
So you know that they're coming from different channels. You know which channels is identified.
This is a different issue. I mean, how you know this channel and this guy just belong to this message? That's a completely different issue. So let's say the whole world is simple. There's one communication, one message, one digest. All right. Now, you know your question: what if you have 1 million messages, 1 million digests? How you know which one is which one, right? Okay. That's a problem. I'll leave it for you to solve. Okay. Okay. So, no, assume it's so simple like this. Okay. We're gonna come to key management later. In chapter 18 or 17 or 16, I forgot. We'll talk about the keys distribution and how this will happen. All right. So let's take a look at the message authentication code in AC. In here, what we need to do, not only make sure that the message is correct, we have to know it's coming from Bob. It's coming from this person. In our case, coming from Alice. All right. So Bob has to check two things. The message is correct and coming from the right person. So what you do in here, you have a message, okay, all right, and it will be encrypted with the key, hash, and you're gonna generate what?
To man.
MAC. So to generate the MAC in here, what did you use?
Key.
The hash function and
The key.
the key. So now what you're gonna send? You're gonna send the message plus the MAC. It was received, and both of them we're gonna go in secure channel. That's fine. Why is encrypted? That's fine. Okay. So you receive the message and the MAC. You will use the key to what? To get the message. Okay. From the message you're gonna get to the MAC, right? And you receive the MAC, you compare the calculated MAC with the received MAC. If they are same, then you know what? The message is integral and authentic. Because you'll not be able to read the message without the key. And the key for who? For Eve. Okay, shared it with who? With Bob. So Bob was Eve, right? It's Eve.
Alice.
Yeah, Alice. Okay, Alice and Bob. So Alice shared her key with Bob, send the message with a hash. The idea of the hash to make sure that the message did not change. And to be able to do that, she has to use a key. Who owns the key? Alice. How Bob knows it? Because Alice shared it with him. All right. So if Bob is able to read the message using the key belongs to Bob, then the message is coming from who? From Bob. All right. So here what we have, message authentication code. So the security of a MAC depends on the security of the underlying hash algorithm. All right. So in here, for example, what you have, okay, a nested MAC. Now that's a simple MAC. What to explain? It could be much more complex. So listed MAC in here, what you have, the key appended to the message, you create the hash. Okay? Then now what you have the hash and you append the key again. And you hash again and you send one MAC. So it will become, this is what we call it, nested MAC. It's much more secure. So you append the key to the MAC, you MAC it again, or you hash it again, and you send it. More secure. Even more secure is the HMAC. HMAC. So what is HMAC? Is you split your message into small messages, B size. Okay, so you divide it in M1, M2, M until Mn. So what is N? Is the total number of small blocks from the message. So you divide your block of message, right? And then after that, you're gonna create the initial one, the M0 from where? From added to the B bits, okay? This will be B bits, and start with from a value, a preset value called IPAD, XOR, and will be filled there. All right. So this is your messages, the message divided into n m's, and you added one here. Then you hash it. All right. So we'll give you n bits. So the size of the hash is n bits. Okay, and that's what we call it, the intermediate HMAC. Then you pass it to here, and you have another padding. This is a preset value. Okay, and you hash it again, and then you have the HMAC. So it's like multiple operations on the data until you get to the data. The CMAC. This CMAC is much more secure. CMAC is like using encryption, right? All right. So again, what you do with the data, you divide it into blocks: M1, M2, M3, and Mn. Right? Usually, you have the message so big, divided into equal blocks. All right. And in here, what we use all of the encryption algorithms. Can you give me an example for encryption algorithm? Dash, 3 dash, triple dash, double dash, AEC, or you could use any encryption algorithm. So encryption algorithm, what does it need? What are the inputs for encryption algorithms? Two things: the data and the key. Okay. So now what you did, the output becomes the input, or XORed with the second block, and then became input for this. So in here we're complicating it, so you keep XORing, okay, and it becomes more complex, right? Okay, and for the last one, okay, what you get XOR is three things: the intermediate value, the last block, and a key, another key. This key is generated from where? From the original key. Start with another encryption technique, and we'll give you a value key that you substitute there, and then by the end you're gonna have what? NBIT CMAC. Right? Remember what we did before when we studied DES, triple DES, ES? We went inside each box and we studied how it works. The same thing. It's like, diffuse and confuse. Diffuse and confuse. Okay, what's the bottom line in here? Okay, what's the difference between encryption and hash functions?
Hash functions with the key that you can able to retrieve the data.
Okay, so one major difference in encryption, the input equals to the output. The size of the message equals the size of the output. So if you have the input is 5,000 bits. What will be the output? 5,000 bits, but different, encrypted, right? In here, the input could be anything, variable, but the output always a digest, which is fixed size. Okay, 512 bits, for example. All right. Number two, all the algorithms, all the encryption algorithms, you need keys. In here, you could have it with a key or without a key. If it's with a key, what we call it? MAC. Okay, Mac short for Macintosh. Macintosh, right? Right? Mac short for Macintosh?
No.
Not today. Okay, not today. Mac short for Message Authentication Code. Alright? That's the second difference. Third difference. Okay? Third difference. What's the third difference? That you have to have 3 criteria for any hash function. Actually, this book uses hash function. I think it's a wrong name. They should say one-way hash function. Okay, usually what we use one-way hash function. Does it go? Okay. But one-way hash function, it has to have the preimage, second preimage, and origin. These are the criteria that they have to have. All right. So let's have a break for 5 minutes, and we'll come to see real hash functions. We're gonna design a real hash functions in the next session. All right. So we'll continue with the cryptographic hash functions. So let's take a look at real hash functions. All right. Okay. I traded hash functions. So there's a model called Marital Damgard scheme. Okay, as you see in here, we can come closer in here. So basically, you have original message. This original message could be any size. It could be any size, right? Okay. So what you have to add to it, you have, because it's any size, you have to know the length of it, and we have to pad. We'll show you how to add the length and how to pad. So you're gonna divide it into M blocks. So M1, M2, until MT, all right? And each block is n bits, whatever, okay? Okay, whatever, number, all right? So you have the compression function. What is the input for a compression function? The message itself, and then the initial hash. Okay, the idea here, you have to give the hash, the digest. So there is a predefined hash function in bits. Okay, you give the message with the initial hash predefined. Okay, this message is predefined, right? You know the message, right? So do the compression function. You do the compression function, you're gonna get H1. Take the message, the second block, with the output from the first stage, you're gonna get H2, H3, H4, until you get to the HT. So the HT is what? The message digest. That's what you get will be the output. Alright? Will be out. So again, in the Marital, the guard, what we do, we take the original message, alright? We divide it into equal blocks, and then we apply the compression technique on these blocks until we get to the message digest. Alright. Clear so far? Okay. So the compression function is made of message digest is of the message. Okay, there is different techniques like we're gonna take so some of them are made from the compression functions. There are compression functions there. Okay, you just use them. Where do you use them? In the block. You use them in the block here. Okay, there's different compression techniques. You could use them in here, or you could use symmetric key block cipher. Like what? Like DES, triple DES, ASE. You're gonna use them in this block in here. So the function in here could be a compression function and could be a cryptographic function. Alright, depends on what we're going to use. Okay, so if you look in here at the SHA, okay, a SHA-1, SHA-224, SHA-256, SHA-384, and SHA-512. So the number represents what?
The bit.
The size of the digest, the output, the digest. Okay? So SHA-1 is not secure anymore. The maximum message size is 2 to the power 64. Alright? The block size is 512. What did we say before in here? We divide the message into
Equal.
blocks.
Equal blocks.
Blocks. So what is the maximum message you could have? 2 to the power 64. What is the size of these blocks?
Equal.
512 in the SHA. 512. The message digest size, okay, the output is, the digest is 160 bits. So you could have like a message which is like 25,000 characters. The digest will be only how much? 160 bits. Always the digest fixed length, fixed length, right? And the number of rounds, remember when we were talking about the cryptographic, we have rounds. How many number of rounds? 80. Okay? And what is the word size? Because what you do inside it, you divide the data into words. The word size is 32. Okay, let's take a look at the most recent one, which is SHA-52. So what is the block, what is the message size, maximum message size? 2 to the power 128, which is a huge. I mean, even in your in a super in your computer will not have that much of data. If you can take all the data in your computer and make them one message, will not be that much. So that is like a huge message. Okay? What is the block size? 1K, 10 to 24. That means when I have the message, I have divided into 1024 bits each. And then we have the message digest size is 512. So what is the output of the output of the algorithm of the hash function?
512.
A digest. What's the size of the digest? 512. Then we have 80 rounds, and we have the word size is 64. All right. So that's exactly how it works. Okay. Okay. This is a few algorithms. So the first one is something called Robin scheme. Robin scheme. You take the message, okay, and you divide it again into blocks. M1, M2 until MT. All right. Then you get it encrypted. So what we have in here, what's the function we have in here? Encryption algorithm, such as this, for example, right? Such as this. So the plain text will be initial value, and the key will be what? The message size. So let me ask you a question. If I'm using this, what M1 size should be? How much is the key for this? You just did your exam last week. That's what's the key size? 64, right? 56, but there is a parity bits. 64, right? 64. So in here, if you are going to use this, how much has to be the block size in here? 64 bits. All right. If you're using AES, what is the block size should be? 128, right? This is size, right? So you use the message as the key, plain text, you're gonna get the cipher. The cipher will be the plain text, this will be the key. Keep going until by the end what you're gonna get? The digest. How many bits is the digest?
64.
M bits. M bits. If it's like this, it's 64, right? Alright. So that's what we call it Robin scheme. Okay? Of course, you know, sometimes the message is not perfect. It's not, you cannot divide it by the side of the block. What do you have to do? You pad it. You pad it, right? What's padding? Adding bits for it. Okay, padded. So this is in here. It's the padded message of T blocks. Alright? If the message you could divide it exactly into T blocks, that's good. You don't have to pad. But if you have to pad, then you have to pad. Right? Then in here, Davis-Mayer scheme. Davis-Mayer scheme. The same thing. The same thing. So you have the padded data in here. Okay. The only difference in here in encrypt. Okay. Okay. Look in here. The difference in here is this is the key and directly. So it's like straightforward. In here we'll make it a little bit complex. So also you add the XOR. In here there is no XOR, right? Now what I did, we took forward from here and we XOR'd in here the output from the first stage with the input in the first stage and became an input for the next stage. We made it a little bit more complex. Little bit more complex. Okay? What's the problem in here? What's the problem in here? The problem in here, if you are able, if you are able to know what's in here, you'll be able maybe you to track it back. In here, a little bit more complex. Again, what's the digest in here? It's the M bits at the end. All right. So this is what we call a Davis-Mayer scheme. Then we go to Matthias-Mayer-Ossius scheme. Same thing. We have the data in here. All right. Remember that the key was from here. Now the key is coming from the initial bits, and the plain text is coming from the message. Still you have the X. So what's the difference between this and the previous one? We flipped. The P was in here, the key was in here. In here the key is coming and the P is coming from there. And by the end we're gonna have the message. This is another one which is the Mayagoshi perennial scheme. Mayagoshi perennial scheme. The same thing, we have the T blocks, all right? But in here, we expanded the XOR, so we XOR not only the input from the previous one to the output of the previous one, also we XOR to it what? The first block. And that, the 3 head will be the input for the next stage, and so on and so forth. So we made it a little bit more complex, all right? Yes, for you now, you're studying how the 4 different techniques work. Okay, and I'm sure you're assuming it becomes more secure, right? Because there's more operations. But always you have to think of the time complexity, the computation complexity of the work. So yes, I mean you could have like much more, but you don't want to have algorithm which is sluggish. It takes forever to do it, right? So definitely the first one, the one we started in here, maybe it will be the most fast, the most simple one, but maybe the least secure. In here, it will be more involving, more secure, but it will need more complexity. Okay? So when you talk about complexity, it could be a software. If it's implemented as software, that means it will be slower. And if it's implemented by hardware, it might be more expensive. Chip, you're creating a chip, right? So all of these factors need to come together. Needs to come together, right? All right. So let's take one example. This book explained 2 algorithms, the SHA and the firewall. Okay, we'll explain only one. I leave the other one for you to enjoy it at home. Okay, if you like. But let's take a look quickly at the SHA 512. If you understand SHA 512, I think you'll be able to do the other ones. Okay. All right. So the SHA 512. Okay. So let me see if you remember. In the SHA 512, what is the digest size? What is the digest size? SHA 25. 512. That's what we call it 512. What is the block size? I'll be surprised if you remember.
64.
1024.
Can you see it? SHA 512? How is the block size? Block size. Is it 512?
1K.
1K, I think. So the block size, where is it? The map, okay, the block size, 1024. Okay. How many rounds we gonna have? 80. What is the digest size? 512. What's the word size? 64. Okay. So
Why? I have question. Why the round size in 224 and 256 more than SHA-1 and less SHA?
that's how they designed it.
Design?
That's how they designed it. Okay. All right. So that's how it is. So let's start in here. So the first thing, we have a message. What we do with the message? Talk to me now. What we do with the message? Divide it into blocks. What is the size of the block? 1024. If I can't divide it into blocks, what I have to do? Padding. I have to do padding. So in here, okay, what we do, we have to have it multiple of 10 and 24 bits blocks. All right? Block 1, block 2, to block and, right? Then what we are using? A compression, not cryptographic, a compression what? Function. The input for the compression function is 512 bits, this initial value, and the output is what? The hash, which is 512. Then this will be fed to the next stage. And will be fed to the next stage. By the end, I'm gonna have 512 bits, which is the digest, the final digest. That's what we send as output, right? So in here, where is the block boxes we have that we need to delve in? We have to know what is the compression function, right? What happens in here? And we have to know what is the initial value in here. Anything else we need to know? Nothing, right? So we have to know what is its value, how is it calculated, and we need to know what's the compression function. So let's go zoom in, right? You agree? All right. So the first thing is SHA-512 insists that the length of the original message be less than 2 to the power 128, which is a huge data. You don't have to worry about that. You don't have to worry about that. It's a huge data that you don't have to worry about that. All right? Now, in here, the other thing for the original message, the last 128 bits will include what? The length of the
Original message.
message. Okay? So you have in here the original message, and you have in here 128 bit you add to it. In between, what you're gonna have? The padding. What is the padding? 1 plus as many zeros you want. What is the condition? That you could divide it into blocks equals to how much? 10 to 24. Alright? So we have a message, padding, and length. What is the size of the length?
The same original message.
The same length of the original message, which is how many bits?
120.
128 bit. What is the size of the original message? Variable. What is the padding? Is a variable. How many blocks you can make out of it. Right? Right? Simple, right? So that's the first, this problem. So what is the number of padding bits if the length of the original message is 2590? So the original message is 2590. So what we need to do, 2590 plus the padding plus the 128, it's divisible by how much? 10 to 24. We say mod 10 to 24. That's what we did in here. So in here, what we say is the message. So basically, what we have to do, okay, the message plus the padding plus 128 mod 1024 equals how much? 0. Alright? I know what the message, how much is the message? 2590 plus P plus 128 mod 1024 equals 0. That means, okay, P equals what? 259 plus 128 mod 1024. You do the math, okay, it will become how much? 354. So if you add the 354 plus the 2590 plus the 128, this will be dividable by 1024. Okay, you're gonna have that. Okay, so that's what it is. Alright, then after that, what we're gonna do, the message now, the sub-message is divided by 24, right? So what we're gonna do, we divide it into the message block and the digest as words. So we're gonna have like the message block, we're gonna create 16 words, each 64 bits. Okay, so each block, where is the blocks? Come on. Each block of these, okay, we're gonna divide it into 16 words. Each word is 64 bits. Okay, so each block 16 words, each word 64. So if you multiply 16 by 64, how much?
1024.
10 and 24. All right. And and the output, so the input, each block will have 16 words. The output will have 8 words, times 64 will be 512. So we name them the words A, B, C, D, E, F, G, and that will be the message digest. Again, the message will be divided into blocks. What's the size of the block? 10 to 24. The block will be divided into 16 words, each words, how many bits?
64.
64. That's it. And we name them A to H. We name them, the output will be named A to H. Alright? Then what you do, word expansion. Now we have to do word expansion. So each word, originally how many bits? 64. We're gonna do expansion, word expansion. How many words we have? 16. We're gonna expand the words to have, how many words? I think we're gonna have 80 words. I think so.
Yeah, 80, yeah.
Yes. So from the 16 words, we're gonna generate how many words? 80 words total. 80 words. Okay? So how we generate the 80 words? The first 16 words is a very simple. The same first 16 words. So you're gonna pass word 0, word 1 until word 15, the first one. Then the next of the words, we have to calculate them. We have to calculate them. How we calculate them? Very simple. Okay, there is an operation. So let's say we have a word in here. Okay? It comes from an XORing 1. The word number, so let's say this is 40. This is word 40. So we're gonna take the word 40 minus 16, how much?
24.
34. And then here we're gonna take the word minus 15, which is 35. What we're gonna do for it, we're gonna rotate shift and then put the result in here. And then we're gonna take the word minus 7. So 40 minus 7, 33, right? And we're gonna take the word minus 2, I think, in here, or 7? 2. So you take the word, okay, and XOR all of them, that will give you the word. Bottom line, without going in details for a second, from the 16 words, we're gonna generate how many? 80 words. The first 16 words will be the same, the rest will be calculated. How they are calculated? By an algorithm given to you. Okay? Who designed this algorithm? The people who designed child 512. Why? Can we ask why? We don't know. That's how it was designed, right? Okay. So if you need to know what is rotate shift, that's the rule for it. If you need to know what's rotate shift in here, that's the rule for it. Okay? Bottom line, we generated from each block how many words? 80. Let me repeat it. So we have a message. We divide the message into blocks. What is the size of the block?
24.
10,
64.
24. Then we take this block, we divide it into 16 words. 16 words. From this 16 words now, so 16 words, now we expand. From this 16 words, we generate how many? 80. 80 words, right? So this is the example. What is the example in here? Okay. Now, what is the value for the initial? Okay, the initial in here, for example. Okay, so let's take a look. You remember in here what we said, that what we need to know. We need to know this, and you need to know what the initial values in here. Initial values. So the initial values are in this table. Okay, in this table. Okay, A0, B0, C0, D0. Like we have how many words? 8 words. How they are calculated? Okay, they took the first 8 prime numbers. What are the first prime numbers? 2, 3, 5, 7, 8. They square rooted. They took the square root. So when you take the square root of 2, it will be a value and the fraction part, right? So they took the first 16-bit, I think, okay, from the fraction part, first 64 bits from the fraction part. Okay. So they took the prime number 2. They took the square root. All right. So what will be the output? For example, 1, 4, 3, 9, 8, 3, 7, 1. Okay. So they convert this to binary. Okay. And they took the first 128-bit, I think, or 64, I forgot. All right. And they convert it to hexa. And that's the value in here. So this is generated from the first prime. This is from the second prime, third prime, and so on and so forth, right? That's how they generate it. And these are preset values, Now, so now we're going to go to the compression function. Where is the compression function? Where is the compression function? So what is the compression? What is the input for the compression function? 80 words. Remember, we took the 1024. What we do? We change it to 16 words. And from 16 words, what we did? Expanded. Expanded to how many? 80 words. All right? Okay? 80 words. Where are we? Here. Okay? And then you pass it to 80 rounds. Round 0 to round 79. 80 rounds until you get to the final. Okay, there is a process in here, of course, inside the round. We'll take around that. So there's another boxes in here. What we do inside the round. Okay? So that's exactly what we do inside the round. Inside the round, what we do, we shovel the box. So A goes to B, B goes to C, D for C goes to D. The only two I have to calculate is the A and the E. How I calculate the A and E? I know you're lost, you're confused. I'm not expecting you to. Okay, I'm just going through it. That in case you go watch the videos again, while you're reading the book, it will be easier for you. But definitely this step, this procedure, you have to read it. You have to keep going back and forth, all right? All right, and it's like, just remember the rule is that you have a bigger picture with boxes inside it. Then we zoom in the picture, in the box, and we see how it works. We'll go inside the box, we'll see a few boxes. We'll go inside the boxes until we get the whole picture, right? So definitely, I promise, when you go read it at home, it will be very easy to go through, all right? All right, so in here, we have to calculate the X and the Y, and these are the rules, all right? These are the rules, you're gonna follow them, okay? And this is the keys for the, okay, so what are these? Are the keys, preset keys for the rounds. How many rounds I have?
80.
80. How many keys I have here? 80. Are you interested to know how they are calculated? They took the first 80 prime numbers and the qubit, the same thing. They took the fraction, converted to bits. They took the first, that's how it is. This is, okay. All right. And they, did the whole process in here. Okay. Right. So let me go back, reverse. This is the other while pool. I leave it for you to read it. Okay. If you like to read it. I mean, one example I think is enough to understand what happens there. But let's go back for this. So what we did in here, this is what are these? These are the keys for the 80 rounds, right? Okay. Okay. And so this is one of the rounds. This is only one round, right? So in the one round, what you do, you shovel the words. Shovel the words. You shuffle the words. The only two words you need to calculate is
X, Y.
the A, which we named it X, and the E. Here is the process. Here is the boxes. Right? Let me go back further. So what is this in here?
From
The function, the compression function. What do you have inside the compression function? 80 rounds. We just came from the rounds, right? 80 rounds. What are the input for each round? The K. Where is the K coming from? From the 80 keys I just showed you, right? So K0 for round 0, do you understand? And the words in the input, right? Okay, this is what is this? This is the compression function. What is this? The 8 initial values. How they are coming from? From square root of the first 8 prime numbers. You take the fraction, you convert the fraction to binary, you take the first 64 bits. You convert it to hexadecimal, that's what it is. Sorry guys. When, you know,
No, it's easy, but when you go back and forth,
Exactly, yes.
it's gonna confuse
So-
you.
when you go back in here, what is this? The word expansion. What is word expansion? That we said we have 16 words. Each block has 16 words. What we have to do with the 16 words? Expand them to how many words?
80.
80 words. That's what we did in here. So in here what we did, we took the block. What is the block? 10 and 24. We divided into 16 words. Alright? My laptop turned off. Alright? There is no power. But we finished. We finished what we want to finish today. I hope that you will find it useful. Was it useful?
Yeah.
I'm sure it was. Alright. Alright, so that's what the hash function, and that's what you use for message integrity and for message authentication. Integrity with no key, authentication with a key. And we took one common hash function, one-way hash function, which is SHA-512, and we show you how it was built A to Z. As a matter of fact, if I give you a homework today to go write a Python code for SHA-512, you have enough information in the chapter how you design it. So you could design it in a way that I'll give you a message and you're gonna get me what? The digest. You have enough information. The only thing that you're gonna need like a week or so to finish the code to run will be a little bit complex. It will be nicer if it's like a hardware. Always, whenever we can to make things by hardware, we will do. It'll be faster. We offload the CPU. We don't need the CPU gets busy doing like encryption and hash function and all of that. Let it be alone, do what it should do. And if we can integrate a chip in the motherboard or in the system to do that, that will be a great thing. All right. So that's the other thing. When you usually choose an algorithm with a cryptographic algorithm or a function, you always want to know what is the possibility that you could build this or that algorithm using hardware. All right, hardware. Most of our laptops and new laptops nowadays, if you go to the BIOS, you could enable the chip there, and you could do the encryption and all this operation, right? So that's how it is. All right. So I think this is what's very useful. So please do that next week. So next week we're gonna talk about a very important thing, which is digital signature. Many of us every day maybe will hear about digital signature, and all of that, but we don't know how how is it built. So you'll understand exactly how digital signature. One more thing we'll cover next week, okay, is today we spoke about message authentication, about entity authentication, okay. So, authenticate entity could include application, it could include servers, login, okay. So how is it done? Using challenge, for example, using challenge response, zero knowledge protocols, sometimes biometrics, different things. How is it done? So we'll talk about this next week. All right. So I think we are progressing very well. I mean, believe me, by the end of the semester, every single or most of the you will have a very, let me put it this way, you will have a very solid knowledge about the concepts and security. Okay. Myself, when I took this course many years back, I remember the professor maybe covered 1/3 what you take in this class. All right. And I know at that time it was too much, all right? But that's how it is. This is a course that you really should know a lot. The student there asked about like keys, right? When you have many keys, how this key this digest belong to this. So we're gonna go after that. We're gonna talk about key management. All of us communicate with thousands of people, or at least we have like thousands of sites that require authentication and all of that and keys. All right, so we're going to talk about, in chapter 15, we're going to talk about the key management. And there is a very nice structure there, okay, for the like X509, if you heard about it. We'll talk about the key management. Okay, so after that, we're going to jump to a very important thing that you have really to realize. Usually what is the name of this course? Network security. It's not cyber security, it's a network security, right? So network means communication, data exchange. So when you talk about communication, how many layers are there in communication? In the OSI reference model? 7. They removed 1. Okay, 7. So 7, right? Starts with the physical, data link, then network, then transport, then 3, we call them the application, right? All right? So when you see the data transmitted from a source to the destination, where do we apply security? Can you guess? Almost all of them. So there is a security at the application level. Can you give me examples? That's what we'll cover, I think, in chapter 16. So for example, if you send an email or whatever, so what kind of security? We have BGP. What's it? PGP? Pretty good privacy. Okay, and there is another system called S-MIME. Okay, this is just an example for security applied for data at what level? At the application level. Then the data gonna go down to where? To the network level or layer. All right, and we apply a different. To the transport layer, and I'm sure all of you have configured his or her email, and you heard about Tls and Ssl, right? So this security, what level? In the transport layer level. Okay. So we'll explain to you exactly how SSL works, which is the older, it's not secure anymore, and the TLS. The TLS, how it works, so how it's applied in the transport layer, all right? And then after that, we'll move down to the next layer, which is the network layer. And the network layer, we're talking about the data between host to router to host. So we're gonna talk about, I'm sure you heard about it, IPsec. IP security. What we do with IP, so for example, you heard about virtual LANs, okay, where you create tunnels tunnels. So the data, for example, so technically, let's say that you have a host in here, your host in here, okay, and your destination in here, all right? So usually how is data is communicated, okay? So the network is what? Is router connected with another router, router, many routers, right? Routers, right? Many routers, right? Okay? And there's a router in here, the home router, and there is a home router for the destination, right? Many routers. So yeah, you know that the data has to go from here, and you know the data has to come from here. But besides that, the data could go like this, or it could go like that. It's dynamic, right? Go like that. Okay, it could go multiple routes. It could go multiple routes. Depends on availability. Exactly like when you go to New York City, you could use Route 15, you could use 95, you could use Route 1, right? So in here, for security, what you do first, okay? Like what you do with virtual LAN, or you do with what they call it, you know, when you create secure communication, what you create? Yes, exactly. What you do, you create a tunnel. So you create a tunnel of data, for example, from here like this, okay? Tunnel. Everything goes through this tunnel is encrypted. So this is security at what level? At the network level. At the network layer level. All right? And of course, there is a security, different security. That's a security for integration. Like for example, in the data link layer, when you send a frame, you include with it CRC. That's only for integrity. For integrity, make sure the frames are integral, that it maintain the integrity of the frame, but it's not for privacy, for example, and all that. So basically, it's okay. So the goal is to tell you network. The course is network security, right? Network security. So we could start it right just from the last 3 chapters, talk about transport layer, network layer, and application layer. Okay? But to be able to go to that point, what you have to learn? What is a cryptography? What is the digital signature? What is, you know, hash functions? What is the, did they say digital signatures? Public key encryption, private key encryption, all of these like a setup. Preparation for you to understand all of that. So be prepared, and by the end of the course, seriously, I mean, you know a great deal of information about network security. Okay, after in the break, just go read again the material, just tie everything together, okay? And when we have the practical labs and all of that, you really feel what security. I mean, you feel what does it mean security. You feel the meaning of all the terms that you read about security. You'll have like a good handle and a grasp of it. All right. So mission still we have like 2 months to go. Hopefully that, you know, by the end you'll feel more confident. Any question? All right. I understand there's a lot of math in here, but you know you cannot do security without math. Exactly. You cannot do food without salt and pepper. Okay, the same thing. All right. You could, but you know. Thank you.
Thank you.